So, we are going to discuss some of the important questions regarding the chapter Magnetic Effects of Electric Current. So, moving into the first 1 mark questions. Name the type of current which is used in household supply and that is given by a cell or a battery. We know the current which we use in our household supply and appliances is AC or alternating current, and that is given by a battery or a cell is DC or direct current. Second question, give one application of electromagnetic induction. We know that electric generator is a device that works on the principle of electromagnetic induction. So, moving to third question, what are magnetic field lines? Justify the following statements. A. Two magnetic field lines never intersect each other. And magnetic field lines basically means they are the field lines which defined as the path along which the unit north pole, that is imaginary, tend to move in a magnetic field if it was free to do so. We know that for a magnet there will be north pole as well as a south pole. So, if such a unit north pole tend to move in a magnetic field, if it was free to do, such a path that is defined along will be called as magnetic field lines. So, the first one, two magnetic field lines never intersect each other. We know that the magnetic lines of force do not cross or intersect each other. If they do so, then at the point of intersection, the two tangents can be drawn at that point, which will indicate that there will be two different directions of same magnetic field. So, the compass needle points in two different directions, which is not possible. So, it's clear that two magnetic field lines never intersect or cross each other. It's obvious from this picture that magnetic field lines never intersect each other. Second section, the magnetic field lines are closed curves. So, from the picture itself, you may be able to analyze that magnetic field lines are closed continuous curves. They emerge from the north pole and they merge at the south pole, isn't it? But they never intersect each other, but they are closed curves. So, they diverge from the north pole of the bar magnet and converge in south pole. So, inside the magnet, they move from south pole to north pole in the opposite direction. So, magnetic field lines are closed curves and never intersect each other. These are some basic properties of magnetic field lines. So, next question, why does a compass needle get deflected when brought near a bar magnet? We know that the compass needle is a small bar magnet itself. So, when a compass needle is brought near a bar magnet, then due to the repulsive force between unlike poles and attraction between the unlike poles, the compass needle is deflected and settled in the direction of the net magnetic field. Moving to the next question, the given magnet is divided into three parts A, B and C as you can see in the figure. Name the parts where the strength of the magnetic field is maximum and minimum. How will the density of magnetic field lines differ at this part? You know the magnet is divided into A, B and C sections. So, the maximum strength will be at the poles or ends of the magnet, which is denoted as A and C. Where will be the minimum strength of the field lines? It will be at the center or at B in case of this particular magnet. Second question, how will the density of magnetic field lines differ at these parts? So, at A and C, magnetic field lines will be crowded, while at B, they will be spread out. How does a solenoid behave like a magnet? Can you determine the north and south poles of a current carrying solenoid with the help of a bar magnet? Explain. So, we know that a coil of many circular turns of insulated copper wire, which is wrapped closely in the shape of a cylinder, is called a solenoid, and that is clearly depicted in the picture given. So, when the current is passed through a solenoid coil, the magnetic field is produced. Why? Because it is due to the presence of turns present in the same direction. As a result, the resultant magnetic field is very strong as well as uniform. So, the solenoid behaves like a strong bar magnet. We can of course determine the poles of magnet which is formed by the solenoid. The end of the solenoid connected with the positive terminal will behave like the south pole, as you can see in the figure, and the end which is connected with the negative terminal will be behaving as the north pole. So, the positive terminal behaves like south pole, negative terminal behaves like north pole. So, the field lines inside the solenoid are in the form of parallel straight lines. This indicates that magnetic field is same at all points inside the solenoid. That is, the field is uniform inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron which is placed inside the coil. Such a magnet which is formed is called as electromagnet. The next question. Name the type of current which is shown by the graphs A and graph B. Name any one source of the current which is shown by graph A and graph B. Third one, what is the frequency of the current in case of B? Write two difference between the current which is shown in both of the graphs. So first question, which is the type of current which is shown by the graphs A and B? It is clear that the type of current which is shown by graph A is a DC or a direct current. So it has only one direction of flow. What about other? The other current which is shown by graph B is changing every time, or it is an AC or alternating current. Second one, what is the sources for the graph A and graph B current form? So a dry cell will be the source of current which is shown by graph A in the form of direct current. But we know that the graph B represents the alternating current or AC. So an AC generator is of course the source of current for the shown in the graph B. So we are asked to calculate the frequency of current in case of graph B. From the graph B, it is clear that time t is equal to 0.02 seconds. So how can we find frequency from the time? We know frequency is equal to 1 by t or the reciprocal, isn't it? So f equals 1 by t. So when you substitute the given value, f equals 1 by 0.02, you would get it as 50 Hz. And now we are asked to mention some of the differences between direct current DC and alternating current AC. So the basic difference is that the magnitude of direct current is constant and flows in one particular direction only. But what in case of alternating current? The magnitude of AC changes with each time and direction of AC reverses periodically. The second point is that direct current cannot be used for large scale supply of electricity for household purpose. But what in case of alternating current? It is used to run electrical appliances like electric bulb, electric heater, electric iron, refrigerators, etc. The frequency of direct current is given as 0. But what in case of alternating current? The frequency of alternating current in our country or India is mainly as 50 Hz. So this is the basic differences between direct current and AC or the alternating current. So moving on to the 5-mark question, two coils C1 and C2 are wrapped around a non-conducting cylinder. Then coil C1 is connected to a battery and key and C2 with galvanometer G to detect the presence of the current. On pressing the key, which is represented by K, the current starts flowing in the coil C1. So we want to state our observation in the galvanometer based on the questions. So what happens when the key K is pressed on? So when the K is pressed on, we know that the key operates, so the galvanometer which detects current will deflect momentarily in one direction. Then when current in the coil C1 is switched off, what happens? So when the current in the coil C1 is switched off, what happens is that the galvanometer needle deflects again momentarily, but it will be in the opposite direction to that in the previous case. And what happens in case of the current is passed continuously through the coil C1, when the current is passed, what happens? So, when the current is passed continuously through the coil C1, we know that the current when passing, there will be no deflection which is observed in the galvanometer. And the final one which is asked is, name and state the phenomenon responsible for the above observation. Write the name of the rule that is used to determine the direction of current which is produced in the phenomenon. So, two coils are connected, there is a galvanometer, there is a key, and when there is one coil which is showing a current, something happens in the other two. So, we need to state and define that particular phenomenon. So, we know that the phenomenon that is responsible for above all observation is electromagnetic induction. So, what was electromagnetic induction? It is a process by which a change in magnetic field in a conductor induces a current in the another conductor which is placed nearby. So, the basic rule that provides it for the electromagnetic induction is Fleming's right hand rule. So, that rule is used to determine the direction of current which is produced in this electromagnetic induction. So, the induced current is found to be highest when direction of motion of coil is at right angles to the magnetic field. In this situation, we can use a simple rule, that is the Fleming's right hand rule. So, from the Fleming's right hand rule, the direction of the induced current will be given by the rule. How does it state? It states that if the thumb, forefinger and the middle finger of the right hand is held in a perpendicular position to each other, then the thumb will point in the direction of the motion of the conductor, the forefinger will point in the direction of the magnetic field, then the middle finger shows the direction of the induced current. So, all this being applying to the three fingers and held in a perpendicular position, then they together contribute to the Fleming's right hand rule. So, finally, if you need to find the direction of induced current in case of electromagnetic induction, you use Fleming's right hand rule. Moving on to the next question, describe an activity to demonstrate the pattern of magnetic field lines around a straight conductor carrying current. So, to describe the activity, the main aim is to study the magnetic field due to a straight current carrying conductor. So, what are the different apparatus required for it? You need a thick conducting wire, a battery, a rheostat, magnetic needle, an ammeter of the range of 0 to 5 ampere, key, a cardboard, a stand to hold the wire, the iron fillings and sprinkler of iron fillings. So, what is the procedure to perform this particular activity? So, from the figure, it is clear that all these apparatus are used. So, first of all, we need to attach a thick wire through a hole in the middle of the cardboard and clamp it in a stand. And now, you have to attach the ends of this wire through a key, variable resistor and an ammeter which show the current on either side of a battery and hold it vertically and perpendicular to the board. Now, we need to spread the iron fillings uniformly on the cardboard and place the magnetic needle on the board. So, the fourth step is we need to close the key and tap the cardboard slightly and observe the orientation of iron fillings. So, what do you observe? You will observe that on closing the key, the iron fillings are aligned in the pattern of concentric circles around the wire. So, we can conclude that the current carrying conductor is a source of magnetic field. The magnetic field is in the form of concentric circles whose center lies on the wire, and that is clearly vivid from the following representation using the figure. So, a pattern of concentric circles indicating the field lines of a magnetic field around a straight conducting wire is formed. The arrows in the circles shows the direction of the field line. So, what is the rule that is being applied in this particular activity? It is clear that it is right hand thumb rule which is used here. If a straight conductor is held in the right hand such way that the thumb points along the direction of the current, then the tips of the fingers or the curls of the fingers shows the direction of magnetic field around it. So the current is shown by the thumb, and the curl of the fingers or the fingers will show the direction of magnetic field. So right hand thumb rule finds a way to show how there is behaviors in case of this particular activity demonstrated.